background. I'm first going to talk about the ideal gas and non-ideal gas. So, talking about ideal gas, in the case of ideal gas, we assume that the gas molecules interact in a very uniform way. They collide perfectly. However, in the real world, gases do not behave ideally. Instead, their behaviors depend largely on pressure and temperature. Therefore, we usually need to correct this assumption of ideal gas by using the compressibility factor. Let me now tell you a little bit about what Z is and what really the why we use the Z factor. So when we have high pressure, the gases don't necessarily behave normally. So I need to put a number in my equation, in my ideal gas law equation, to correct for this difference in behavior. This Z number is a Z factor, and my equation changes from PV equals nRT to PV equals nRTZ, where I include Z to account for the non-ideal behavior of gases, of the gas, which one sees at very high temperatures / pressures. So let me now also tell you about the compressibility factor and how that's important and how we can determine properties from that. So I'll be referring to this figure in this part. So let's say we have some water and we start to increase the temperature. So right here, let's say we have water. This is a diagram, and we have water, and we increase the temperature. As we increase the temperature, the water will go from the liquid phase into the vapor phase. But now, if we increase the pressure, the water would move from the vapor phase into the liquid phase. This line right here is the liquid vapor line. So if we increase both the pressure and temperature at the same time, I will eventually reach a point called the critical point. At this point, which is this point right here, so at which the water is neither liquid nor vapor, in a different phase called the supercritical phase. The supercritical phase is up right here. This phase has both properties of liquid and vapor at the same time. So this point that determines the transition is called the critical point and is defined by the critical temperature and critical pressure. And these values are normally through experimentation and are found in the back of our chemical engineering book. So in the chemical engineering problem, when we're given a temperature and pressure, what we do is we plug that pressure into our two special equations for reduced pressure and reduced temperature. Reduced properties are a special way of finding the Z factor on the chart. So in our book, we have critical temperatures and critical pressures of different species. So if I was to pick one, let me just read one example to you. Ethane has a critical temperature of 305.4 and a critical pressure of 48.74. So using those values, as I said, I would plug them into this equation, the critical pressure and the critical temperature, knowing my pressure and knowing my temperature, and I'd find my reduced values. Once I find my reduced values, and on my Lee-Kessler's chart, the x-axis is reduced pressure, and the y-axis is the Z factor, and these lines right here are the reduced temperature values. So we correspond the reduced pressure value to a reduced temperature value, and as we draw this line to our y-axis, we find what the z value is on the y-axis.